Hello everyone and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over the final part of chapter 14 in Zumdahl, the 7th edition. It's about acids and bases, so hopefully this is the last video. So section 14.7 is about polyprotic acids. So polyprotic means multiple protons. And so what we're really thinking of here are acids like carbonic acid or phosphoric acid, where you have multiple hydrogens that can be donated. So acids that can furnish more than one proton when they're undergoing a dissociation, they're called polyprotic acids. So the nice thing about a polyprotic acid is that it always dissociates in a stepwise manner. So you only lose one hydrogen at a time. You don't lose both at once, or in this case, all three at once. Okay, so that's always nice to know. And keep in mind that the conjugate base that you form from that very first dissociation equilibrium step becomes the acid in your next step. So in reality, if you have, two protons to donate, there are two acid-base reactions that are happening, one right after the other. Or if you have three, if you're a triprotic acid like this, you would have, three steps to your equilibrium here. Now, for a typically weak polyprotic acid, which, again, that's all we're really going to be dealing with, the Ka of the very first step in our acid-base equilibrium step here is going to be the largest, and then it's going to get smaller and smaller as you continue to remove a hydrogen from each one. And so typically speaking, only the very first dissociation step is important to pH, because if you have a very large drop off in the second or third Ka value, for the second or the third proton being removed, then only the first one is really going to be giving us what we would think of as the hydrogen or hydronium ion concentration for that particular reaction. So here's a good example, right? We have a question that asks us to find the pH of a 1 molar solution of phosphoric acid, and it gives us, because it's a polyprotic, or in this case, triprotic, because there are three, acid, we've got all three Ka values here. And you can see that there's a very large drop off as we go from 1 to 2. And then not so big, or not such a big drop off between 2 and 3 here, but that very first one's a huge drop. So here's the first reaction, right? I've got my acid, I've got my base, I've got my conjugate base and my conjugate acid. So now this conjugate base becomes the acid for the next step. And now again, I've got another conjugate base and another conjugate acid here. So now this becomes our conjugate acid for the last step until I get all the way down to phosphate. So in reality, this is the actual real important equilibrium. Yes, these are happening to minor degrees, but because the Ka values are so little, they're not really happening very much. So only the first Ka matters. And I basically just explained why. Huge drop off though, right? Now, if I wanted to find the pH, what would I do? I would need an ICE diagram. So I have my 1 molar solution that I was given at the very beginning, minus x here. I had none to begin with, and now I'm increasing by x. So now, if I'm writing just the first Ka value here, I have my, dihydrogen phosphate ion, hydronium divided by phosphoric acid. And remember, our rule says that if, this number here is less than 1 times 10 to the negative 3, I'm pretty much allowed to ignore the minus x part from this. And if that doesn't ring a bell, go to part 2 or go to part 1. It's explained in more detail there. Now, this is very, very close to 1 times 10 to the negative 3 here. So I'm actually going to say, yes, we can use it. So we're just going to do, our Ka equals x squared divided by the initial concentration of 1. We're going to say, okay, I multiply these two together, I get 0.0075. So I want to take the square root of that number. When I take the square root of that number, I get 0.0866. I do the negative log of that number, and I get 1.06. So how big of a difference would we get if we included that minus x and we did this using the quadratic formula instead? If you use the quadratic formula, you get 1.08. So pretty close, a pretty good approximation still. Again, if you don't believe me, you can add the minus x and solve using the quadratic equation instead, like we did in chapter 13. So again, if you need a review or a refresher on the quadratic equation, feel free to go to chapter 13's video because that's where we went through the whole quadratic equation step and stuff. All right, now here's where this is a really annoying question, but it's a good question. Calculate the equilibrium concentration of phosphate in a 1 molar solution of phosphoric acid. How much phosphate is there floating around? Look how little that Ka is. It's going to be tiny because remember, this is the major equilibrium that's happening. This is happening even less frequently. This is happening even less frequently. We're going to get such a tiny amount of phosphate out of this. It's going to probably be an extremely tiny number, okay, just based on um, logic, if that makes any sense. Okay, so let's go back to our previous ICE diagram because that gives us our X. Okay, so remember this is what we had on our previous slide. So remember that the conjugate acid for the next step is what this is. So our conjugate base becomes our conjugate acid for our next step. So really I need to know the amount of this. And so that was 0.0866. Technically also, I need to know how much hydronium ions we have because all of the hydronium ions are coming from this first step. It's like there's such a small amount of hydronium ion coming from, step 2 and step 3 of that polyprotic acid base equilibrium that we're not really going to have it affect anything. Almost all of the hydronium ion, in fact, we can basically say all of the hydronium ions that are being manufactured come from this first equilibrium step. Okay, so now why did I go back there? Because now what we want to do is, instead of using the letter X, I'm going to use the letter Y. We want to repeat this again. So now I'm going to start with what I was given, 0.0866. That was what I found in the last problem. So subtracting Y. Here I have my hydronium ion concentration. It was the same. These were equal. Plus Y. I don't know how much of this there's going to be, how much hydrogen phosphate there would be. And so I can still set this up. I know my second Ka value is this. So this would be Y. This would be 0.0866 plus Y. This would be 0.0866 minus Y. Now we can actually do a shortcut here. And I want to kind of like prove it to you again. So yes, this is an extremely tiny number. So I feel very confident saying this minus Y is going to be negligible. Why is the plus Y going to be negligible? Basically for the same reason. The amount of Y that we're going to have is so little, it's not really going to have an effect on this at all. Remember, almost all of the hydronium ion that was made already was made in the first step. We're not really gaining any extra, hydronium ions from this particular second step. So I'm going to say we can ignore this minus Y and we can ignore this plus Y. So it makes it way easier. I have this. So this cancels already. So Y is literally equal to the equilibrium constant. That's kind of nice. All right, but we have to do it again because phosphate is, in the third step. All right, so this is the amount of hydrogen phosphate that we had from our last step. I'm going to be, again, losing some amount of that. We had no phosphate to start with at the beginning of this process. Our H3O plus concentration is the same. And now we have our new, or our last Ka value here. So Z would go here, 0.088866 plus Z would go here. Our equilibrium constant minus Z would be right here, right? And so now I'm going to do the exact same thing. I'm going to assume this is tiny and assume that that is also tiny. So we're going to ignore them. And now we're going to be able to plug everything in. So I'm going to be basically multiplying these two by each other. So it's going to be tiny. And then I'm going to divide it by that number. And so we end up with 3 times 10 to the negative 20. That is ridiculously tiny. And that would be the amount of phosphate ion that we would have in there. Now, again, if you used, the quadratic equation instead of estimating, you're going to end up with a different answer for this. But it's still going to be a ridiculously small number. That's kind of the point of this, is that when we have, a polyprotic acid, each step of that polyprotic acid dissociation, really the first one is the important one that actually makes the big difference. The second or the third, if there is a third like there was for this particular example, doesn't really have an overall effect. All right, let's talk about salts. So when we're talking about salts and whether or not they're acidic, basic, or neutral, what we're really talking about are ionic compounds. So ionic compounds, remember, are governed by our solubility rules, because when you dissolve salt in water or a salt in water, again, when I say salt, I don't mean just sodium chloride. You know, you can have different effects. It can make an acidic solution a basic solution, or it could be completely neutral. And so, because when dissolved in water, they break up into ions, those ions can behave as acids or as bases. And so, the general rule here is that the salt of a strong acid and a strong base gives a neutral solution. So if I have K and Cl, that is the salt of potassium hydroxide here and hydrochloric acid, right? The K would have come from conceivably the sodium hydroxide, or sorry, potassium hydroxide. The Cl would have come from hydrochloric acid. So remember, K plus and Cl minus are extremely, extremely weak. This would be the weakest of acids. This would be the weakest of bases. So when you put them together, you actually end up making an overall neutral solution. And that applies to, again, any strong acid and strong base that you'd mix together. Any salt from that reaction would end up making something extremely weak. So this would be like, from nitric acid, a nitrate ion. This would be sodium from sodium hydroxide. You put them together, what do you get? Sodium nitrate, and you get a very, very neutral solution when you mix them together. Now, basic solutions form if the anion of the salt is a conjugate base of a weak acid. So if you have a weak acid and, as a result of that, you would make this conjugate base, that conjugate base would make a basic solution. So, hydrofluoric acid, when dissolved, right, you make a fluoride ion. So something with a fluoride ion is going to make something weakly, is going to make a weakly basic solution. Acetate, an acetate ion from, acetic acid is going to end up making something that is very weakly basic. And something that we never actually mentioned is that how are Ka and Kb related to each other? If you multiply Ka and Kb for a particular compound, you end up getting the Kw for water. And so Kb is what we use when we're starting with a base, but you can also find the Ka of a base. So Kb and Ka times each other ends up making 1 times 10 to the negative 14. And so that's for basic solutions. Now, what about acidic solutions? If we have a cation of a salt that is the conjugate acid of a weak base, now what we end up with is the opposite. We end up with an acidic solution as a result. So you can imagine ammonia, when mixed with water, it forms ammonium ions. And so ammonium ions are weakly acidic. And we would start with Ka when we're dealing with something like, a weak acid. But again, if you multiply Ka by Kb, you get 1 times 10 to the negative 14. All right, so here's kind of a loose chart that gives you the relationship between whether or not a solution with a particular salt is going to be acidic, basic, or neutral. So if we have a neutral cation and a neutral anion, we end up with a neutral solution. And so when we say neutral, we mean, again, a salt of a strong acid, strong base reaction, okay? So think of all of your strong acids, any of those anions, and think of your strong bases, any of those cations. When you mix them together, that makes a neutral solution. Now, what if your cation is neutral, but your anion is a conjugate base of a weak acid? That makes a basic solution. What if you're a conjugate acid of a weak base and your anion is from, again, neutral? Then we would end up with an acidic solution. And then what if you have, a mixture of, a conjugate acid of a weak base and a conjugate acid of a weak acid? Then it really depends on your Ka and Kb values. So then you'd have to figure it out. So let's actually take a look, like it says here, at the qualitative predictions of pH of solutions. So if the Ka is greater than the Kb, that means that you're going to have an acidic solution. If the Kb is greater than the Ka, then that means that the pH is going to be basic. If the K and the Kb are equal, then that would mean 7. So let's figure out how we can utilize this. So I have acetic acid or vinegar. The Ka is 1.8 times 10 to the negative 5. I have hydrogen cyanide. Again, Ka is 6.2 times 10 to the negative 10. What would be the Kb values for these anions here, for just acetate and just cyanide? Well, I can do that by division, right? So I take my Kw, I divide by the Ka, that gives me the Kb. So that would be the Kb for acetate. Pretty low. What about Cn? Again, same thing. I get 1.6 times 10 to the negative 5. So another question that isn't really on the screen, which of these is a stronger than base, acetate or cyanide? Answer, cyanide is. Then which of these would be a stronger acid? And again, you guessed it, it would be acetic acid is much stronger. Why? Because remember, the stronger your acid is, the weaker its conjugate base becomes. And again, that's from part one. Or maybe part two. I think it was part one, though. So go back to part one if you have any questions about that concept. All right, so another good question is arrange the following 1.0 molar solutions from lowest to highest pH. And so justify your answer. So we take a look at all of these, and most of the time we do exactly what it would say, right? We would find the pH of these solutions. That's going to take a really long time, and we're going to have to go through a lot of ICE diagrams in order to do this. So instead, the nice thing is we can look at the Ka and Kb values for these particular items. So first thing I would say to do is take a look at Ka and Kb values and just use logic because they're all the same concentration. So they can all be compared directly by just looking at the Ka and the Kb values. So what kind of, materials or what kind of molecules do we have here? So here's what I would say to do first. So if we're taking a look at each one of these, let's color code acids, acidic cations, neutral solutions, basic anions, and bases. That'll give us the general flow, right? Because acids would have the lowest pH, and then next would have, our acidic cations, neutral would be in the middle, basic anions, and then bases. That'll give us an idea. So first things first, what are our acids? We have hydrobromic acid, hydrofluoric acid, and hydrogen cyanide. Those would be our acids. Where are our acidic cations? Well, I only see one. Do you see that one too? NH4Cl. So NH4 would be an acidic cation. Cl or chloride is just from, again, a reaction between hydrochloric acid and some other strong base, right? So that's where the Cl is. Now, neutral solutions. Again, I only see one. This is the product of sodium hydroxide and hydrochloric acid, right? We've got the Na plus from the sodium hydroxide. We've got the Cl minus from our hydrochloric acid. So that would mean that that would be completely neutral. What about our basic anions? Maybe saying anions is a little misleading here. Definitely NaCN, right? So sodium cyanide, that's going to be a basic anion, the CN coming from hydrogen cyanide. But NH3 isn't really a basic anion, but we know that it forms NH4 plus, so it must be a base. I just didn't have like a really good classification system for that one. I guess I could have put it as just a base, but it's not a strong base or anything that you needed to memorize, right? Because it's a weak base. So last but not least, we have sodium hydroxide. We know for sure that's just a regular old base. So now let's figure out what order they go in. So obviously the yellow or orange ones are going to come first, then this one, then this one, then the blue, and then finally the purple. But is there some order we can put them in? Well, remember, HBr is a strong acid, so it has to go first. It's going to have the lowest pH no matter what. What about HF versus HCN? We'd have to take a look at the Ka values. So HF has 7.2 times 10 to the negative 4. That means that it would go next. HCN would go after that. It is a much weaker acid. Okay, after that, we have NH4Cl. And take a look at that, right? We've got 5.6 times 10 to the negative 10. So, let me go back. So if we take a look again here, by general logic, we end up with, kind of the right answer here. Next up, we have our NaCl. That has to be neutral, so it has to have a pH of 7. What about our blue ones? We'd have to take a look here. you can see they're very close in Kb value. And remember, the lower the Kb value, the more weakly basic it is, right? So that would mean that, NaCN would come first, and then very closely after it would be ammonia. And then after that, we have NaOH, which is a strong base, so it has to appear at the end. So if we were to put them in order, this is the order that we would put them in. So we would put our strong acid, we would look at the Kb values for the rest of our acids. This is, ammonium ion, which is making it slightly acidic. This is our neutral one. So, this is our neutral one. So we've got NaCl. After that, we've got our two weak bases, which again, these are very close to one another. This being a weaker base slightly, this being a slightly stronger base, and then this is definitely one of our strong bases at the end. So even without having to calculate the pH value for every single one of these, we could actually make some informed decisions, which would make it pretty useful for us, especially on like an AP exam. All right, what about this? Consider a 0.30 molar solution of sodium fluoride. The Ka value of hydrogen fluoride or hydrofluoric acid is 7.2 times 10 to the negative 4. What are the major species in this reaction? Well, remember, NaF is going to dissolve in water. So what could we make as a result of that, and what would happen? Well, NaF would dissolve into this cation, so a sodium cation, and fluoride, an anion. Water would also be present because we're dissolving something. Now, why do you think NaF is not considered a major species in that particular reaction? Well, remember, our solubility rules state that alkali metal salts dissolve in water, right? So since we have sodium fluoride, that means that sodium fluoride can't appear in the solution anywhere. So in reality, we're kind of limited to really only two possible reactions. One, where the Na plus mixes with water to make some products, or where the fluoride ion mixes with water in order to make products. As always, there's a possibility that water self-ionizes, and that's the dominant reaction. But again, that hasn't been the case for any of the examples we've done, except for one example. I believe it was in part one, where we were looking at such a small amount of a strong acid and so much water that we ended up with, the Kw being the overwhelming important part of our reaction for that particular example. So here are kind of our three possibilities. So F minus could mix with water in order to make HF and OH minus. That's a possibility. Or Na plus could mix with H2O to make NaOH and a hydronium ion, or water could self-ionize. Now, of these three, why is reaction 2 impossible? I'll give you a pause for that. Take a look at it. I'm making in this reaction a strong base. That's impossible. You could never take water and a cation and make a strong base or a strong acid. So 2 is immediately crossed off of our list. And like I said, our self-ionization of water, that kind of balanced equation, that's never really the answer. Unless we're looking at, again, the example from all the way back in part one, where we had such a tiny, tiny, tiny amount, like a drop of acid in a whole bathtub full of water, where, the water was the dominant part of that acid-base equilibrium. So how do we decide? Well, F minus is going to be our dominant acid-base equilibrium here. But if I wanted to prove it, right? Remember, we were given what HF's what the Ka of HF was. So if I take Kw divide by this, that will give me the Kb of F minus. And we can see it's 1.39 times 10 to the negative 11. And remember, if we compare that to the Kw, which is 1 times 10 to the negative 14, this is the overwhelming winner for our reaction here. So that must mean that this is our actual reaction that's happening in our example. Now, what if I was asked to calculate something like the pH of a 0.75 molar aqueous solution of sodium cyanide. And they gave me the Ka for hydrogen cyanide. I should be able to figure that out, right? So Cn is the conjugate base of this. So first things first, what are the major species in our solution? We should have mostly Na plus and Cn minus. Why? Remember that sodium salts, so alkali metal salts, are soluble in water. That means that Na plus and Cn minus is going to, dissociate. And water, of course, is always present in these situations. Why isn't NaCN, like I just said? It is soluble in water, which means that it's going to completely dissolve. And remember, we're looking at salts. That's this entire section is all about salts. So, of course, we're looking at things that dissolve in water. Now, what are our possibilities? Again, we could have Cn minus or Na plus, making our dominant, having our dominant pole for our equilibrium here. Again, which of these reactions is most likely to occur? We can cross out number 2 because it's making a strong base. We can also cross out number 3 because it's the self-ionization of water. So the top one here is going to be our winner. Now, again, it's giving me the Ka. I really need the Kb though. So I would take our Kw, 1 times 10 to the negative 14, divide by the Ka, and that gives me the Kb. So again, not bad, 1.6 times 10 to the negative 5. So now let's do an ICE diagram for this. So I have 0.75 minus x. Water doesn't count. Right here I have 0 and 0. So plus x plus x. Again, just like all of the previous examples, I plug that into my equilibrium expression. So I've got HCN here, that would be x. I've got OH minus, that would go here. I've got 0.75 on the bottom. And just like before, I can ignore the minus x because this is such a small number. And so I would do 1.6 times 10 to the negative 5 times 0.75, and that would give me x squared. So x is 0.0035. Remember, this is giving me hydroxide ion concentration, though. So that means that if I take the negative log of it, I'm going to get the POH, and it asks me for the pH. So 14 minus 2.46 is 11.54, and that would be the answer. Again, a lot of steps, a lot of logic, but as long as you know the general process, you can start to put this all together. What about the structure of acid-base properties? So is this, important for the AP exam? No, but it does give us an idea of how we can tell what type of bonds we're looking at in like a really complicated structure. So 2 factors to look at when we're looking at the acidity of some sort of compound here. So bond polarity and bond strength. High is good for bond polarity, right? That means it's going to stick together. And bond strength low is good because that means it's going to want to donate. It's going to want to donate its hydrogen in this case if you want to look at acidity. So here is kind of our trend in bond strength. Notice that the bond strength for HF is very high. That's the reason why hydrofluoric acid is actually a weak acid. So hydrochloric, hydrobromic, and hydroiodic acid are all strong acids, primarily because their bond strength is less. And so it's easier for them to, kind of cleave this bond and lose a hydrogen as a result. Hydrofluoric acid is a little bit too high on that list. What about an oxyacid? An oxyacid is just an acid group that has something attached to an OH. Most of the time when we think of OH, again, everybody thinks hydroxide, hydroxide. But no, in an oxyacid, which there are plenty of examples of oxyacids, most of the acids that we come across are oxyacids, like acetic acid and carbonic acid and sulfuric acid, nitric acid. The H attached to the O, that H is the one that we're really interested in because that's the one that's going to become cleaved off, and the H is going to, get donated to water to make hydronium. So for a given series that we're looking at, generally speaking, the number of oxygen atoms as it increases attached to the central atom, the stronger the acid is. And so part of that appears to be that it is a greater ability for X to draw electrons towards itself, meaning that the acidity of the molecule is a lot higher as a result. So a good example of that would be perchloric acid. So perchloric acid is a strong acid. Notice that it has 3 oxygens, and it also has an OH attached directly to the center. Chloric acid has 1 less oxygen, but it's still a strong acid. And then as we lose oxygens, we get to chlorous acid and hypochlorous acid. And these two are really weak acids. So it seems like there's a trend where if we have our central atom here and we're looking at oxygens attached to them, that we have an ability to kind of say there's a connection between how many oxygens that are attached to your central atom and whether or not you have a stronger acid or not. Right here, we've got, again, sulfuric acid. You can see we have two OHs here. It's a diprotic or a polyprotic acid. And so we've got, 4 oxygens here, 2 of which have H's attached to them. Whereas sulfurous acid, H2SO3, we only have, we have 3 instead. And so sulfuric acid is a strong acid, whereas sulfurous acid is not. And that trend continues with nitric versus nitrous acid. And so, again, just kind of a general trend that you might notice. Also, these are not correct Lewis dot structures for this. They're just showing the bonding. So please don't think that's the correct structure for any of these. Lewis acids and Lewis bases. All right, so 14.11. We skipped 14.10. That's not on the AP exam. So 14.11, Lewis acids and Lewis bases. So we've talked about Bronsted-Lowry acids and bases pretty much the entire time. That's how we get equilibrium expressions, all of that fun stuff. We've also talked about Arrhenius acids and bases, like at the very beginning. I said in part 1 there was a third example of a definition of acids and bases, and it took all the way until the very end for us to do it. But it's called a Lewis acid and base. And yes, Lewis meaning Lewis dot structure, named after the same guy, Gilbert Lewis. So what is a Lewis acid? It's an electron pair acceptor, meaning it accepts a pair of electrons, whereas a Lewis base is an electron pair donor. And so a good example of that would be we've got an aluminum ion and we've got 6 water molecules, and it's going to form a complex with the aluminum here. So you can see that a bond forms between here and here. And in the process, which one of these items, molecules, ions, etc., are donating a pair of electrons. So take a look, right? This is the one that's donating, so that's our Lewis base. This is acting as a base. This is the one that's accepting a pair of electrons, so it becomes our acid. And so this complex, this ligonated complex, is an example of, a Lewis acid-base reaction product. Okay? And so, again, a summary of all of the 3. Arrhenius produces hydronium ions, or H+. Arrhenius bases, they produce hydroxide ions. Bronsted-Lowry donate hydrogens. Bronsted-Lowry bases accept hydrogens. Notice that the first 2 involve hydrogens. What if you're given an item that doesn't have hydrogens in it? That's normally when a Lewis acid or base definition needs to be used. So a Lewis acid accepts a pair of electrons, whereas a Lewis base donates a pair of electrons. So a good example would be this. I've got like an oxide ion, and here I've got, it looks like sulfur trioxide, and I'm making a sulfate ion. So there's no hydrogens here. How do I figure out which one of these 2 is going to be our acid or our base? So here, this would be our base. You can see that a pair of electrons needs to be donated in order to form a bond. And then, electrons get moved around in order to make another double bond. But still, this would be our Lewis acid. So this would be our base because it is donating a pair of electrons. This would be our Lewis acid because it is accepting a pair of electrons. And this would be our product. It also works for things with hydrogens, though. It's just, not hydrogens being donated, right? So take a look here, right? We've got BF3 and we've got ammonia. So boron trifluoride here is going to be basically making a bond between our ammonia to make this complex. So it's kind of obvious because this is missing a pair of electrons and this has a pair of electrons. But again, if we use our Lewis acid-base model as our example, this is our Lewis acid because it is, taking a pair of electrons. And then this is our Lewis base because it is donating a pair of electrons here. And so that's what makes that complex work. And so we're technically done. Section, 14.12 is really just a summary. And so we've covered a lot. So What do you need to do when you're looking at an acid-base equilibrium problem? The first thing you need to ask yourself, what exactly is the important part of the problem? What are the major species, aka the ions, the molecules that are floating around in your solution, and how does that influence the behavior of, the reaction? So always ask yourself, what's present? Do we have a strong acid or a strong base so that we can assume the reaction goes to completion? Or do we have a weak acid or a weak base where the reaction does not go to completion and we have mostly reactants? What type of equilibrium dominates the solution, in other words, right? These are kind of the same question. And so always let the problem kind of guide you so that you're able to understand, great, what do I do next? Always remember to reread the question a ton, because a lot of times people will accidentally not answer the question. They'll go through a whole ICE diagram, and then at the very end, you get an answer, you get an X, right? X equals this. It was not asking what X equals. It's asking for the pOH, or it's asking for the pH, or it's asking for a Ka value for something. Like, you always need to make sure that you actually reread the original question. All right, probably the longest chapter we've gone through. If you have any questions, let me know, leave a comment, and our next chapter will be coming up shortly.